everyone, and happy first e-learning day. I hope everyone is doing well and is healthy and safe at home. This is going to be our first video for our e-learning week. We're doing segment lengths in circles. So you need to make sure I gave you those notes last week before we left. Make sure you have the segment lengths in circles notes in front of you. And you also need your green sheet. So if you need to grab those, go ahead and pause the video and get those materials. Today we're doing learning target 4. I can apply segment relationships whose vertices lie inside or outside the circle. Our first theorem for today is the chord-chord segment theorem. If two chords intersect in the interior of a circle, then the product of the lengths of the segments of one chord is equal to the product of the lengths of the segment of the second chord. Make sure you fill these words in on your notes. Now, that's a lot of words for something that's not that complicated. What it's really saying is I have two chords in my diagram. I have A, C, and D, B. They intersect. Their vertex is inside the circle. So I have to take the part of AC, the first part, which is AE, and product means to multiply. So I'm going to take the length of AE and I'm going to multiply it with the length of EC. And that's going to be equal to the parts of my other chord. So one part of DB is DE. So if I take the length of DE and I multiply it with the length of EB, which is the other part, that will give me the equation, the setup I need to solve. Now I think of this as a part times a part equals a part times a part. Because that's all I'm doing. I'm taking the parts of one segment, multiplying them, and equaling it to the parts of the other segments, and still multiplying. Now this next part that I'm going to do is why this theorem works, why this theorem is a thing. It's not how we're going to do the problems, but I want to make sure you understand where this theorem comes from. So what I'm going to do is I'm going to draw in these segments, and it's going to create two triangles. Okay. When I do that, I have these two angles here. Both those angles are inscribed. Their vertex is on the circle. And they both open up to the same arc BC. And we learned a theorem last week that if the inscribed angles both open up or intercept the same arc, then they have to be congruent. So I know those two green angles are going to be the same measure. And that goes for these two angles because they both open up to arc AD. So now I have two triangles that have two angles congruent, which proves that they are similar. So triangle AEB is similar to triangle DEC by angle-angle similarity. And if you remember from our similarity unit, if I have two triangles that are similar, that means their sides are proportional. And I can set up ratios and set them equal to each other and solve for missing values. So I can set up AE over DE, because they are corresponding sides of the two triangles. And that's going to be equal to BE, because they're from the same triangle. AE and BE are from the same triangle, over its corresponding side, EC. And if you remember, to solve proportions, I cross multiply. So when I go to cross multiply, I have AE times EC equals BE times DE. And that is the same equation I have right there. So all you need to know is the theorem. You need to know part times a part, but that's why that theorem works. Our next theorem is secant-secant segments. If two secant segments share the same endpoint outside a circle, then the product of the lengths of one secant segment and its external segment equals the product of the lengths of the other secant segment and its external segment. And again, that is just a lot of words for a theorem that isn't that difficult. Make sure you fill these words in, though, on your guided notes. All this is saying is I'm going to take the length of my tangent, my secant, AC, and I'm going to multiply it by the part that's outside the circle. That's what external means, outside, right there. So I'm going to multiply by BC. And that's going to be equal to the same process, but on the other secant line. So I'm going to take the whole secant, CE, and I'm going to multiply by the external segment, so the part that's on the outside, which is DC. When I do this, I think of this theorem as a whole times the outside. So the whole secant times the outside segment. So whole times outside equals whole times outside. Our next theorem is a secant-tangent segment. If a secant segment and a tangent segment share an endpoint outside the circle, then the product of the lengths of the secant segment and its external segment equals the square of the length of the tangent segment. I'll show you why it's a square, but please fill these words in on your guided notes. So this theorem is actually the same as the other one. I'm still taking the whole times the outside. Okay, so I'm taking the whole secant or tangent, depending on which line it is, times the outside portion of that line, so the outside segment. The whole times the outside equals the whole times the outside. Now, I'm going to focus on BD. BD is my secant line because it intersects the circle twice. The whole of that secant line is BD, so I'm going to take BD, and I'm going to multiply it by its outside segment, which is BC. That is going to be equal to the tangent line. So now the whole tangent in relation to the circle is AB. And I'm going to multiply it by the outside. Well, in this case, because it's a tangent line, the whole tangent is the outside. And that's where that square comes from. Because if I were to simplify this, this is just BD times BC. But because I have two ABs, it's just like having x times x. Well, that equals x squared. So here, that equals AB squared. Now it's time to get your circles reference sheet. You're going to flip to the back. There are two boxes that we need to fill in. And it's very important that you see that this says segment measures, because these relationships are only for when I'm trying to find segments. The diagrams look very similar to when I'm trying to find angles, but the problem is going to ask for segment lengths and not angle measures. So if my vertex is inside the circle, a chord intersects a chord, my relationship is going to be BF times FC. So those two equals DF times FE. Okay, and this is a part times a part equals a part times a part. When the vertex is outside the circle, regardless if it's two secants or it's a secant and a tangent, it's still the whole times the outside. Okay. So for the diagram that I have two secants. So I'm going to do the whole CD times the outside portion, which is CF, and that's going to equal the whole of the other secant, which is CE, times the outside portion, which is CG. So that is a part times a whole equals a part times a whole. Just keep in mind when I do tangent in a secant, tangents are going to be the part and the whole. Oh, I'm sorry, I don't want to put part. Let's erase that. Let's do that again. I apologize. I want whole times the outside. Equals the whole times the outside. All right, so I urge you to pause the video and try example 1. Try all 4 of those problems. And then return the video on and see how I do them and see if I match what you have. All right, so now that you've tried the problems, let's go through them. In A, I have my vertex inside the circle, so that's how I know that I'm going to do a part times a part because I'm finding a segment, I'm finding x. So I'm doing part times a part equals a part times a part. Okay. So my first part is 8 and 6, so I'm going to do 8 times 6, and that is going to equal my other two parts, which is x and 4. X times 4. When I do that, 8 times 6 is 48, and 4 times x is 4x. Divide 4, and x equals 12. In the next problem, my vertex is outside the circle, so I am thinking whole times the outside equals whole times the outside. So I start and I look at AB. My whole is going to be 12 plus 4, which is 16, and the outside part is 4. So I'm going to do 16 times 4 is equal, and then I do the whole of BC. Well, the whole is x, and the part is x. So in this case, I'm going to have x times x. 16 times 4 is 64, and x times x is x squared. And to undo the square, I need to square root both sides. I don't have to worry about plus or minus because x represents the whole length. So my x equals 8. My next problem, my vertex is inside. And they want me to find this whole length x here. What I notice is that I have tick marks, so this is also 5. And because my vertex is in the inside, I'm doing a part times a part. So I can do 5 times 5. And that's going to be equal to the two parts of the other chord, which are 2 and x, which gives me 2x. 5 times 5 is 25. Divide 2, and I get 12 and a half. My next problem, the vertex is on the outside. So I'm doing the whole times the outside equals the whole times the outside. So my whole for the first segment here is 18, and my outside is 5. So I'm going to do 18 times 5. And that is going to be equal to my whole of the other secant, which is x. And my outside is 4. So I'm going to do x times 4. 18 times 5 is 90, and x times 4 is 4x. I divide 4, and I get 22 and a half equals x. Example 2 is a little special. My vertex is on the outside, so I know I'm doing the whole times the outside equals the whole times the outside. So my whole is x plus 12, and my outside is x. But I have a tangent line, so that means the whole is x plus 4, and the outside is also x plus 4, so I'm going to use it twice. So I have my outside times my whole equals my outside times my whole. Now over here, I distribute the x to both terms, so I get x squared plus 12x. And here we have to double distribute. Please don't write x squared plus 16. Okay? Make sure you double distribute. We've talked about this a couple times already. So x times x is x squared. I get 4x plus 4x, which gives me 8x. And then 4 times 4 is 16. Now that I see x squareds, I think quadratics. I'm like, oh no, I got to factor. Well, I have to get everything to one side then. So when I subtract x squareds to both sides, they actually go away. So I end up with a linear equation that's very easy to solve because all I have to do is subtract 8x to the other side, and I get 4x equals 16. Divide by 4, and x equals 4. So the key here in this problem is when you have a binomial times a binomial, what I'm talking about is this right here, make sure that you double distribute. Do not write x squared plus 16 because you will miss this middle term. And then you'll get the problem wrong. We have one last example. I know this video is a little long. I apologize. In the figure to the right, let 8p equal x and pq equal x plus 2 and qb equal x plus 4. CP equals 2, and BD equals 6x, EQ equals y, and QD equals 14. And they want you to find all the missing segments, links. Well, if I do that, I need to know what x and y are. So I need to find x and y. So I look at this. I want to avoid any type of system. We don't want two variables in an equation. So if I do anything and I get two variables in an equation, it's probably not the first step. So what I look at is, I could just pick one variable. I could pick y, but the problem with y is on this line, and it's on this one. And that gives me x and y in my equation, and I want to avoid that. So instead of starting with y, I'm going to start with x. There are x's on this line, and there are x's on this line. And those are two chords. The vertex is inside the circle, so I know I can take a part times a part, and it equals a part times a part. So one of the parts, AP, is x. And its other part are actually these two added together. So x plus 2 plus x plus 4. Okay, and then if I look at CD, I'm doing 2 times 6x. So I get 2x plus 6 when I combine like terms. And 2 times 6x is 12x. And I know I need to distribute this. Now when I do that, I get 2x squared plus 6x equals 12x. And what I notice is that I have an x squared, which means it's a quadratic. And not only do I have the x squared, but I have the x, which means I have to factor. And for me to be able to factor, I need it to equal 0. So I'm going to move that 12x to the other side by subtracting, and I get negative 6x. Now, normally when we move stuff over, we have to factor. I have 3 terms. And then I take my c, find the factors that multiply to be it, and add to be my b. But I don't have a c. Okay, I only have 2 terms. So when I see that, I think GCF. What can I pull out of both terms? Well, I can divide 2 and 6 by 2. It's the biggest number I can divide both of them by without a decimal. And I notice that both terms at least have one x, so I can take out an x. When I do that, I divide this by 2x. So 2 divided by 2 is 1. And if I had 2 x's and I took away an x, I only have an x left. And then I have negative 6 divided by 2, which is negative 3. And there is an x, but I'm taking it away, so there's no x's left. And from here, it's just like normal. I set each one equal to 0, each factor, and I solve for x. Over here, x is just going to equal 0, which is an extraneous solution because I can't have a length of 0. And over here, x is going to equal 3. So now I know x equals 3. So this length is 3, this length is 5, and this length is 7. And now I can loop back, and I can find my y's. Because now I'm going to use this, because I know all those lengths. And I have my y here. And the y chord, the ED chord, intersects that chord, AB. So that's why I'm going to use those 2. Now, the vertex is inside the circle, which means I'm still doing a part times a part. So I'm doing y times 14 equals, for AB, one of my parts is 7, and the other one is 5 plus 3, which is 8. So I get 14y equals 56. And when I divide 14, I get 4 for y. And that's the length of that segment. So now I found all the segment lengths. Oops, I lied. This one is 18. Now I found all the segment lengths. There are some homework problems that you can do now, so if you want to go to your homework and practice these problems, I would suggest you do. If you have any questions, feel free to comment on this post in the Google Stream, and I will answer your questions. I hope you guys have a good day.